Good afternoon, everyone. I'm so happy to be here presenting our work, Privacy Preserving Federated Recurrent Neural Networks, and it's a joint work with Abdurrahman Dia, Apostolos Pirges, Jean-Philippe Bossois, and Jean-Pierre Hubo. And I think I'm kind of lucky to be the last one in the session because Udi and Melek already introduced a lot of the primitives such as the federated learning or homomorphic encryption or packing that I'm going to actually present in this talk. But either way, I'll present them because otherwise it's going to be too short and you can go over them. So in many of the application fields where machine learning models are used, data collection is really important. And I think we now all agree that data centralization and data sharing is very difficult because of the security and privacy concerns such as GDPR and HIPAA and also personal reasons or security of the databases. For this reason, collective learning methods such as federated learning has gained quite a popularity over the last decade, where in federated learning, as Melek explained, the parties keep their data, but they train local machine learning models, and in each iteration, these models are aggregated through some central server, and then the global model is updated and sent back to the parties for the next iteration of the federated learning. And it's, at a first glance, it looks like it provides data protection for the parties here because the data never leaves the premises. But recent research actually shows that federated learning also leaks information about the parties' training data through several attacks that we can apply on the gradients that are exchanged or the global model that is passed to the parties in each of the federated learning iteration. For this reason, several other works employ different security and privacy mechanisms, such as the works that employ multi-party computation, secret share the parties' data over some computing nodes, and these computing nodes are then responsible for training the machine learning model, but these solutions usually comes with high communication overheads, and other solutions employ differential privacy in the federated learning setting where the parties and the server exchange differentially private intermediate values. But as other talks also pointed out, differential privacy degrades the utility, and usually training machine learning models require high privacy budgets. And other works employ homomorphic encryption, where the parties can encrypt their data and send the encrypted data to some central server, and the server can perform the machine learning training on the encrypted data. But these type of solutions are prone to single point of failure and also comes with high computational cost, where other solutions try to alleviate this computational cost by relying on multi-party homomorphic encryption, where instead of sending the encrypted data, this time the model and the intermediate values are in encrypted form, and they always remain under encryption in the federated learning setting. But these solutions introduce several functionality which are limited to generalized linear models, feed-forward neural networks, and several biomedical applications, and we rely on the same setting, but we extend this solution to recurrent neural networks while providing end-to-end protection of the parties' training data, the resulting model, and the query's evaluation data, which is used in the prediction step. For this, we build a system called growth, and we rely on several building blocks, such as multi-party homomorphic encryption, recurrent neural networks, and federated learning. And I'll quickly go over the multi-party homomorphic encryption and recurrent neural networks, but I already introduced federated learning. And in multi-party homomorphic encryption, it is similar to homomorphic encryption, which is enabling computations on encrypted data, but in this one, there is a public collective key that is known by all the parties, but the secret key, which is used in the decryption, is distributed among the parties, such that decryption requires collaboration between the parties in the system. And in this work, we rely on a CKKS variant of the MHE scheme. And what is important for the rest of the talk is that nonlinear functions are not computable under encryption. And we can encode up to m values, which Udi already mentioned in the first talk, which is usually referred as packing, and it is really important to choose a packing scheme because it introduces single interaction, multiple data operations. and recurrent neural networks are a special type of models that enable learning on sequential data such as time series data, and a typical RNN is composed of an input layer which takes a sequential input of t time steps. There's a hidden layer and an output layer, and here I introduced the formula for the feed-forward pass of a simple RNN, which is usually called Elmo networks. And as you can see, the operations that we need are matrix multiplications, some additions, and some activation functions here, which is applied to the layer values. So in our system, there are n data providers, each locally holding its own data, and they want to collectively train a recurrent neural network model. And we assume there is a querier that wants to query the end model to obtain the prediction result on its own evaluation data, which is also private. And we rely on a passive adversary model with collisions of up to n-1 parties. And this means even if n-1 parties in our system collude, they shouldn't infer any information about the remaining parties' data or the model. So I'd like to mention the overview of our solution. Let's say there are 4 hospitals that collectively train a recurrent neural network model. They start with the setup phase, where they generate the cryptographic keys and the machine learning model and encrypt this model. So after this phase, the model and any intermediate value exchanged in between the parties remain always under encryption. And in the local computation phase, by using the encrypted global model, parties perform local iterations to compute the gradients, and these gradients are then aggregated in the aggregation phase, and the model is updated in the model update phase, which is exactly the same as the federated learning pipeline, but all the operations are under encryption. And this continues for several training iterations. And after the training, the parties can agree on decrypting the model, or they can keep the model under encryption. And either case, we enable oblivious predictions, meaning a querier can encrypt its data with the collective key of the hospitals or the parties, send the encrypted data. One of the parties can perform the prediction under encryption, and by relying on a functionality called collective key switching, we switch the encryption key of the results such that only querier can decrypt the end result. And RNN training, even in clear text data, of course, comes with several challenges, and the first one for that is RNN training is not very suitable for parallelization because of the sequential operations, where batch learning is really important because it speeds up the process, and there is the inherent exploding or vanishing gradients problem, and one of the solutions for that is gradient clipping. And I won't go into the details of the contributions, but in this work, to alleviate these challenges under encryption, we introduced several contributions. For the exploding gradients, we approximate the gradient clipping, which is not computable under encryption, by relying on 2 different functions such as tanh and soft clips. And we observed that for several degrees of approximation of the clipping, our approximation behaves similarly to the original clipping function. And we also evaluate with different degrees of the polynomials how our approximation affects the training pipeline. For the efficient matrix operations, which are used for the batch learning, we rely on multidimensional packing and block matrix arithmetic, which is actually similar to what Udi introduced in the first talk, where for n by n matrix, we choose a divisor of L and take each block coming from this matrix and pack and encrypt them into several ciphertexts, such that one ciphertext, which is shown in the 3rd dimension here, encrypts several blocks coming from different matrices. And we can encrypt a lot of matrices in this way. And what is more important is that this block matrix and multidimensional packing preserves the matrix multiplication and transpose operations. And for the multiplication and transpose, we rely on Jiang et al.'s approach and integrating it into our packing scheme. And lastly, for the activation functions that are nonlinear and not computable under encryption, we rely on minimax approximation and evaluate the effect of these approximation in our training. So if we implement ROAD in Go with using Latigo library, which is for multi-part homomorphic encryption operations, and we use ONNET and Mininet for the decentralized system and for building a virtual network. And each part in our setting has this type of hardware specifications. And we evaluate the performance of our system using several data sets. Here I show just 2 of them. And also with even and imbalance setting, which is shown as E and I on the x-axis with 5 or 20 time steps in each of the data sets. And we show here that ROAD achieves really similar model performance to the ones that are centralized training or distributed not secure, which is the vanilla federated learning approach, using original functions without encryption. And there is accuracy or model performance gain from the red bar, which shows the independent training, where the parties train their own machine learning models without collaborating with others. And we also evaluate the scalability of our approach with different parameters. Here I show just 3 of them. And we observe when we increase the number of parties while also increasing the number of data samples globally, the computation time remains almost constant, but the communication scales linearly because of the collective functions that we rely on. In the second plot, we show that the hidden dimension of the recurrent neural network model up until some certain point does not affect the computation time, but after that point, we see almost a quadratic increase in the computation. And in the last plot, we show that the number of features has almost no effect on the computation time because the number of features only affect the plain text operations in the first layer because the input is plain text on the local premises of the parties, and the ciphertext multiplications and the operations just dominates the other operations, and we don't see any effect of the increasing number of features. As a conclusion, we present the building blocks that enable privacy-preserving training and evaluation of recurrent neural networks in the federated learning setting. And by relying on multi-part homomorphic encryption, we perform the computations under encryption without seeing the data. And there is no need to transfer the data because we rely on federated learning. And the model or any intermediate value is always under encryption. And we show that model performance with ROAD is really close to non-secure solutions or centralized solutions. And the building blocks that we present in this paper also apply to several RNN variants such as LSTMs and GRUs. And thank you. I'd be happy to answer questions.
Thanks, Sinem. So we have a highly upvoted question. How were the nonlinear functions computed? Polynomial approximation?
For the nonlinear operations, such as, depends on the function, but for example, sigmoid, we directly rely on minimax approximation. And for example, ReLU, which is like a piecewise function, we approximate the soft ReLU, which has a really similar shape to original ReLU function. And again, we use the min-max approximation on top of that.
Okay, thanks. Is the approximate gradient clipping suitable for DP?
Yeah, this is a question that I frequently get. Well, this is not designed to integrate the differential privacy mechanism, but it can be. The only problem would be, I think, to compute the sensitivity because we don't see anything under encryption and to decide on the thresholds for the clipping. But as long as there's clipping that works with approximated one, I think you can do whatever you want with the approximation.
Okay, thanks. So let me think how to summarize a rather long question. How were the scheme parameters chosen and the multiplicative depth chosen, given the fact that when we train a model, we initially don't know how many epochs we need ahead of time?
Right, so for the number of epochs before we go into the cryptographic parameters, we just fix them before starting the training. And we choose the cryptographic parameters such that if I'm not wrong, it gives 9 levels initially. The plain text scale was 2 to the 31, and the ring degree should be 2 to the 14. And that's right, we don't know the number of epochs, but as long as we know the number of levels and where to bootstrap, I guess the person asking the question knows about where to bootstrap and that's why he is asking this question. We just, implement everything depending on that chosen level.
Okay, thanks. I hope it helps to the one who asked the question, because I'm not able to judge. Did you use any ciphertext refreshing during the training?
Yes.
Okay, and with that we finish.